All right, we've stated the fundamental theorem of calculus, and now we've also seen the proof. Let's actually go through and look at how we would use the theorem. So, to start with, I want to put some examples up. So, we want to evaluate the following. And notice that we're not told how to evaluate. So we talked about before that sometimes you might be asked to use the definition or use geometry. Likewise, use the fundamental theorem of calculus. If we're not prompted to do that, we can choose how to evaluate it. And if there's more than one way that we could go about evaluating any of the following, I think we'll find that actually using the fundamental theorem of calculus would be the most efficient. So the first two examples are actually identical to the ones that we covered in our definition of the definite integral. So we've seen these evaluated using the definition. We've also seen them evaluated using geometry. And now I just want to compare that with using this new theorem. So the first of these is the integral from 3 to 8 of the constant function f of x equals 2. So what we have to do if I use FTC is we want to find an antiderivative of 2. So 2x would suffice. And then notation-wise, what we typically do is indicate that we have to evaluate this from a to b. So in this case, from 3 to 8, and I put those values on this evaluation bar. And then I have to take this function evaluated at 8 and subtract from it what I get when I evaluate at 3. So we get 16 minus 6, and we end up at 10, which you can verify is exactly what we got in the other methods that we used for evaluating. We also looked at the integral from 1 to 4 of the linear function, 2 minus x. A suitable antiderivative here would be 2x minus x squared over 2. And again, I want to evaluate this from x equals 1 to 4. So I have to plug in first 4 and then subtract what I get when I plug in 1. And then I want to clean this up a little and simplifying my answer. So in this first set here, 2 times 4 is 8. And then we have minus 16 over 2, which is also 8. And then 2 times 1 is 1, minus 1/2. And so we end up with 0 minus 3/2. And so we get negative 3/2. Again, that matches what we found in a previous lecture video. So let's look at two examples that we haven't gone through in other methods. So first of all, the integral from 0 to pi of sine of x. Again, I want to think of an antiderivative. We could use minus cosine of x. We want to evaluate that from x equals 0 to pi, and we get minus cosine of pi minus a negative cosine of 0. So we want to be really careful here in these subtractions to make sure we're keeping track of our negative signs. So minus cosine of pi, that's minus negative 1. Cosine of pi is negative 1, and I have negative cosine. And then minus cosine of 0. Cosine of 0 is 1. Minus cosine of 0 is minus 1. So this actually simplifies to positive 2. And then finally, if we look at the integral from 0 to 1 of e to the minus 2x, then here we might have to be a little bit more careful in coming up with an antiderivative. I will refer to this as almost guess and check. And I'll also point out that in our next topic, so not this set of lecture videos, we're going to discuss integration techniques, and we'll see that this is suitable for u substitution. For the moment, though, I can guess the antiderivative. First of all, anytime I encounter an exponential function, I'm tempted to think about an antiderivative involving that same exponential function. What we can do here is pause and think about what the derivative of this e to the minus 2x would be, since I'm guessing that as capital F. The derivative would give me e to the minus 2x, but it would also bring out a negative 2. So because there is no negative 2 in my integrand, I'm going to balance that by putting a minus 1/2 out front. And so we can check the derivative of this function is in fact e to the minus 2x. So we evaluate this from x equals 0 to 1. So we're looking at, I'm going to bring that constant out front, minus 1/2, and I have e to the minus 2 times 1 minus e to the minus 2 times 0. So we get minus 1/2 times e to the minus 2 minus e to the 0, which is 1. Okay, so I want to point out a couple places where FTC is not useful. So at this point, it looks pretty great if we look back at these 4 examples and we see the ease with which we were able to evaluate these integrals. So when FTC 1 is not useful, so a big one is going to be when the function we want to integrate, so the integrand, is not continuous somewhere in our interval. So as soon as there's at least one discontinuity, that's going to be problematic. So a classic example of this would be if we were asked to take the integral from minus 1 to 1 of 1 over x squared. This is not going to be equivalent to simply thinking that, well, an antiderivative here would be minus 1 over x, and we can evaluate it at our bounds to get minus 2. So again, just to emphasize, this is not equal. We can see right away why that would be problematic if you think back to our interpretation of the integral. The function 1 over x squared is going to look something like this. So one thing I can guarantee is that because that function is always positive, I should never end up with a negative for the definite integral. So the key thing here, though, is that what we shouldn't have done is applied the fundamental theorem of calculus, because that assumes that our integrand function is continuous everywhere within our interval. So the problem we see here is this function has a discontinuity at x equals 0. To be clear, if we were asked to evaluate this from, say, 1 to 3, we would have no problem. We could apply the fundamental theorem of calculus. So it's not just the function that is the focus, but also how it behaves over our interval. It turns out that this is an example of what we call an improper integral. That's going to be something we cover in the future. So at this point, the only expectation is that you can spot these cases where we shouldn't be using the fundamental theorem of calculus, but we have not yet talked about how you would proceed in those cases. The other thing to consider is that there is also something that we're kind of assuming that we can do when we encounter these. So FTC is also not useful when we don't know an antiderivative of our integrand. So a classic example of this, if we were asked to find the integral from 0 to 1 of e to the x squared. It turns out that e to the x squared is a function for which you cannot find an antiderivative in terms of elementary functions. So what I mean by that is that if you took a couple minutes here and tried to guess some functions that you thought were an antiderivative of this, then if you went back and took the derivative of those, you'd find that you can't end up at e to the x squared. So a lot of people want to introduce an x in there, maybe in the denominator, but the quotient rule would not get us back to e to the x squared. I will say it's hard to look at a function and know, oh, this is one of those cases where I can't find the antiderivative. So that takes some experience, but this is a classic example. And so in this instance, of course, if I can't find an antiderivative, using the fundamental theorem of calculus is not going to help me. I will say in the alternative here, we could still use Riemann sums, and in fact, that's what computers would do to come up with a numerical answer for this. So there are instances where we can't use the fundamental theorem of calculus. And then I just want to go through one last example. This is going to bring this back to some things we looked at with our definition of the definite integral, but kind of add an extra layer to what we can do with that. So we're back to when we can use FTC in a helpful manner. So here you're asked to evaluate the limit as n approaches infinity of the sum from k equals 1 to n of e to the 1 plus k over n times 1 over n. Again, I'll point out that it doesn't say how we have to evaluate this. If I actually try to evaluate this limit by writing out the sigma notation and trying to find the limit, that's going to be really, really challenging. So it's not telling me how I have to go about this. So what can be advantageous is if I notice that that looks like the limit of a Riemann sum. So the goal here is to first express this limit as some appropriate definite integral. So that we've had practice with. We had that in our lecture on definition of the definite integral. The difference is now we can actually use the fact that those are connected as a way to evaluate complicated limits like this, where we're actually going to use the fundamental theorem of calculus. And again, if that is unclear, hopefully it will be clear by the end of this example. So the key thing is I noticed that that looks like I could perhaps express it as a definite integral. And then my process of doing that mirrors what we saw before. So keep in mind that what we want to do is identify different pieces. So the first thing we talked about is looking for delta x. So when I come back to my sigma notation, the key thing that jumps out to me is that this could be delta x, because remember, delta x always has to be a constant divided by n. So we're going to choose that piece to be delta x. And consequently, the rest of this has to be f of xk. Again, if I'm viewing this as a right-hand sum. So we also know that if delta x is 1 over n, x sub k, which we've defined as a plus k delta x, would be a plus k over n. So when we come back to what we're looking at here, we need to have e to the 1 plus k over n equals f of xk, which now we can say is f of a plus k over n. And if you recall, we get to choose the pairing of a and the suitable f of x for which this is true. So I've gone through this before that you can make several choices. And again, just to reiterate that, I'll go through some different choices here. So what if we choose, so again, coming back that I want these two to be equal. Looking at what I see there, a natural choice would be, say, a equals 1. And if I do that, then we're trying to say that e to the 1 plus k over n equals now f of 1 plus k over n. And the goal is to figure out what f of x would look like. Remember that what I look for here is the input and what happens to it. So I see that this function f seems to take my input and put it in the exponent of my exponential function. So the function looks like it would be e to the x. Then we can say that the original limit is now equivalent to a definite integral of the function e to the x. And let's pause here and remember our bounds. Our bounds come from our choice of a, which we said here was 1. And to find b, I always come back to my delta x and remember that the numerator is the length of the interval. So this has interval length 1, meaning b would have to be, 2. And so this is similar to what we saw before. I'm able to express this limit now as a definite integral, the connection there being the definition of the definite integral. But if the goal is to evaluate the limit, that's asking us to find a number. And now if I've made this connection, if I can find the number that this definite integral equals, I've consequently found the number that this limit approaches. So that's where I want to use FTC and kind of following through with the rest of this. So now I find the antiderivative of, or n antiderivative of our function. It's e to the x. I evaluate it from 1 to 2. And so we find e squared minus e to the first power. So we have now shown that this very complicated limit actually evaluates to e squared minus e. And I'll point out that we didn't, in fact, take a limit anywhere. The connection was the definition of the definite integral. And I'll end this here with just an alternative. So again, that's a complete solution to this example, but one could take several paths to get there. What if we had instead chosen, say, a equals 0? If I come back up to this last bullet point and substitute in a equals 0, we're trying to take e to the 1 plus k over n and now equate it to f of 0 plus k over n. Whoops. So when you think about what f of x would be, again, track the input k over n. It looks like, whoops, the function here should be e to the 1 plus x. So if I were to go about it this way, when I start with the given limit, then we're going to say that that could also be written as equivalent to now the integral of the function e to the 1 plus x, but my bounds are different. Here we've selected a to be 0. The length of my interval, which is dependent on delta x, that hasn't changed. That's still 1. It's just that that means b is 1 now. So to evaluate this integral, notice that e to the 1 plus x is e to the 1 times e to the x. E is just a constant, so my antiderivative here is e times e to the x. So I could evaluate this from 0 to 1 and get e times e to the 1 minus e to the 0, which is e times e minus 1, which is e squared minus e. We get the same exact answer here. And again, that kind of gives more verification that I said before, that you can get the correct answer with many, many different ways of choosing your a value. And so you'll have a little bit more practice with this now, with the added benefit that we can take it all the way to the value that the limit approaches. And really, we're taking advantage of FTC in that final step.